coupling it. This catalytic cycle, you should be familiar with the style of this now. We always begin with an oxidative addition. We always end with a reductive elimination. And the difference between the reactions is just what's going on in here. So you do an oxidative addition so that you've got your organic group and the leaving group both attached to palladium, which is now palladium 2. You then do, it's written here metathesis, but you could call it transmetallation or exchange. So, actually, no, this isn't quite the transmetallation, I beg your pardon. This is, sorry, I beg your pardon, this is a ligand exchange. So often these are done with an alkoxide base. I was forgetting for a moment. And so you exchange your halide or triflate ligand for an alkoxy ligand. Then you get the transmetallation. What the group that is the group that you're coupling to is attached to boron and becomes attached to palladium, and the alkoxy group here becomes attached to boron. Now in this case, the boron derivative, which is a bit different to the tin or zinc or magnesium derivatives, the boron derivative needs to react with a base to become a borate. So it needs to be, that's a B- species. So now 4 groups around the boron. That's necessary because that makes the loss from the boron of one of the groups much more favourable. Boron as a Lewis acid likes to accept electron-rich groups and then donate groups. So it's accepting an alkoxide from a base and then donating, not the alkoxide back again, but a different group. So boron, if you like, is seesawing between tri-coordinate, 4-coordinate with a minus charge, and back again. So it's adding one group and then giving a different one up. But the result is that the group that was on the borate derivative ends up on the palladium. And then, of course, if you've got the 2 groups you need on the palladium, might need to add in some more ligand, but whatever happens, there's a reductive elimination, which is the coupling process, and the palladium 0 is regenerated. So in this case, compared to the tin, magnesium and zinc cases, we're replacing those metals by the pseudo-metal boron, but we are making sure the boron is actually going in as a 4-coordinate borate species into the transmetallation. This Suzuki reaction tends to be more popular than the others because the zinc and magnesium derivatives are not so stable, and the tin derivatives in the Stille reaction, whilst relatively stable, industry doesn't like them so much because you end up with tin residues in your product. And tin is toxic, and it's difficult to remove the tin to a level at which the regulators find it acceptable. Boron doesn't have that problem. There are therapeutic agents out there with boron in already, so having boron around is not regarded as too much of a problem. Of course, you don't want lots of it, but normal purification methods suffice there. So that's the Suzuki-Miura coupling mechanism. Same kinds of couplings, and we'll have some examples of that later on in tomorrow's final session, I think. The other reaction that I would mention is the Sonogashira reaction. This is a specific reaction for terminal alkynes coupling to, well, again, organic group with a leaving group on. That's the same as we've seen all the way through. But here we're using palladium and a copper 1 derivative to do a coupling. Similar sorts of groups attached to for R1 and R2. Not so easy for alkyl groups here. So here's an example of a double Sonogashira reaction, where we've got a bromide here and a bromide at the other end of the molecule, and silylated ethyne derivative, acetylene derivative. Palladium is in there, copper 1 is in there, and you get this coupling product. Here's another one with this alkenyl bromide and a terminal alkyne, palladium derivative, copper 1 derivative, coupling to make that bond. And once again, the geometry of the alkenyl halide is retained in the coupling. So the coupling takes place where the leaving group was. So what's the mechanism here? What's the additional bit from the copper? So palladium 0 complex again, oxidative addition, should be familiar with this by now, believed again to be a 14 electron complex. Then the transmetallation happens from an alkynyl copper, copper acetylide. Where did that come from? Well, our initial alkyne comes in at the bottom here. Copper complexes to that, sideways on. That, in the presence of base, you get an elimination of the terminal position of terminal hydrogen on the alkyne, which is moderately acidic, and the anion, to pair with the anion that is introduced with the copper, and that gives you the alkenyl copper. When that transmetallites, then you're getting the copper 1 back, and the anion is the anion that came from the original leaving group with component R1. And then, so it's not so different to what we've seen before, it's just specific for alkynes, acetylenes. That gives you a complex with the alkyne and the other organic group trans to one another, pseudo-rotation if necessary, and then reductive elimination to do the coupling, regenerates the palladium 0. So it's essentially the same process as all the others, but this has the specific variation of putting in the alkyne, and that this works well with copper because of making the copper acetylide or copper alkyne complex. So that all those family of reactions are all very similar to one another, those palladium ones. Now, while we're on palladium, I want to talk about a family of reactions generated separately by Buchwald and Hartwig in the States, which is where the nucleophile is now a heteroatom, a nitrogen or an oxygen. So this is about doing effectively nucleophilic substitutions on a benzene ring. Now you should know that you can't normally do that. You normally react benzenes with electrophiles to do substitutions. But this is how do you put in a nitrogen or oxygen heteroatom? Well, you can do it if you have a traditional leaving group on the aromatic system and with a palladium catalyst. So this is a useful way of making new CN bonds to aromatic systems or CO bonds to aromatic systems. So here's one with, actually this is showing selectivity. So bromo-iodobenzene, the iodide is the more reactive of the bonds. So that's the one where the palladium goes, and that's the one therefore that couples. It's coupling with this pyrrolidine derivative. So the nitrogen is acting as the nucleophile, if you like, as the coupling partner. So it's got palladium 0 complex as it happens. There's some base present as well. And then there's solvents and ligands, other ligands for the palladium. Here's another one where you've got bromobenzene and this chloroaniline. The bromide is the most reactive of the C halogen bonds, so that's where the palladium oxidatively adds, and then nitrogen is the nucleophile, so you've got palladium and a base in the system again, and you get a new amine or a new aniline derivative. Because if you think about it, there's no simple way of directly making an N to aromatic or O to aromatic bond. If you want to make an N to aromatic bond, traditionally you nitrate, reduce to amino. Which of course is quite vigorous conditions, but these are relatively mild conditions. So how is that happening? Well, should be beginning to look familiar by now. Palladium 0 complex, oxidative addition, insertion of the palladium into the bond between your aromatic ring and your leaving group, your halide usually. Exchange or coordination, I should say, of an amine to that palladium. Base then, I'm sorry this green does not really show very well, but that's a metal tertiary butoxide, a metal alkoxide base, and that's effectively doing an exchange of that's exchanging out the, taking out an H from the amine and the X, which was the leaving group that you put in, and that allows the amine to complex as an amide ligand to the palladium. So effectively the base is fixing the nitrogen onto the palladium. And then everything's set up to do the reductive elimination, and round you go again. So we've made the aromatic to nitrogen bond via the having both ends coordinated to the palladium. Now the bit that's in grey there is going to be the difference, the slight variation on this cycle if, well, I beg your pardon. The bit that's going to come in grey that I'm going to emphasise in a moment is because Hartwig himself reckons that there are two possible pathways going on here. So this is one where we're coordinating the nitrogen first, and then the base is linking it fully to the palladium. The other option is if you kind of reverse the steps. So bring in the base first to as a ligand to the palladium, and again the metal halide is dropping out, and then do an exchange of nitrogen for oxygen on the palladium. So it really is doing the two steps. Instead of amine first followed by alkoxide, this is alkoxide first followed by amine. And it's believed that both of those pathways operate. So here we're saying alkoxide exchange for the leaving group that was on our aromatic ring, and then the alkoxide is substituted by the amine. whatever happens, you end up, whichever sequence it is, you end up with a palladium-2 complex with the aromatic ring and the amide ligand both attach the palladium, and then a reductive elimination takes you back around to regenerate or complete the coupling and regenerate the palladium 0. So when you're looking at these, always remember that you're going to start with an oxidative addition somehow. You're going to do reductive elimination at the end to get your catalyst back, and somewhere in the middle there's going to be some exchange processes, maybe a transmetallation here, exchange of nitrogen for some other ligand in whatever sequence. Right, we'll see some more examples of that perhaps later on. Before leaving this palladium area, I want to talk about CH activation, which has achieved a lot of prominence in the last 5 years or so. And this is a term that's actually been used to cover quite a number of different possible mechanisms. And that says at the bottom here, the mechanism is often not well understood. There's actually also a mistake on this slide, because here it looks as if nothing's happened. Actually, this should have, instead of, I think this is a copy and paste without ever changing it, this alkenyl group here should now be sitting off this position here. One way of thinking about how, so this is about how you activate CH positions, because obviously in the couplings we've looked at so far, it's usually been a leaving group, a CX bond that we're coupling. But CH activation is talking about where there isn't an obvious leaving group, but still metal couplings can actually get around that. Now, of course, you can't select any old CH and do a reaction at it. There's usually some reason. And one way it can happen is if it is effectively an aromatic electrophilic substitution. So let's say you're using a palladium-2 complex, you could regard that as an electrophile. So here could be a pyrrole or an indole or something like that. You could say it's palladium-2 as the electrophile, adding, which leaves, this is a sort of a sort of nitration of benzene type of mechanism, that then loses a proton. So you've done an electrophilic substitution there. And then you do a coupling reaction. So that's given you your organopalladium derivative. Then you might do a coupling reaction. So here, this is meant to be a Heck reaction. So that's why this alkene should be actually fastened on this position. That's a cut and paste error, because it looks like nothing's happening, and that's not true. So that's one way you could get an organopalladium species without having to have a leaving group there. So you just treat it as if it's a palladium-2 as an electrophile, and as if it is electrophilic substitution on an aromatic ring. It could be that it's a sort of neighboring group participation effect. So, or a directing group assisted metallation. This effectively is a neighboring group. So if, for example, you have this benzene ring which has a pyridine ring attached, then the palladium can be effectively guided in by complexing to this nitrogen potential ligand, and that can actually influence the palladium to insert into the CH bond. And so that, without worrying too much about the detailed mechanism, it's really it's the idea of having an adjacent group that is directing in your palladium, and so it's the that is what gets the palladium into that adjacent position. How exactly the palladium is getting in there instead of the CH, that may be by the electrophilic substitution mechanism. As I say, mechanism is often not well understood, but the ultimate result is you functionalize just one position out of the other CHs around this ring, and you're functionalizing the position that can be reached by a palladium complexing on the nitrogen. So if you look at these CH activation, if you see these CH activations, there's usually some reason why a particular position has been selected. Either it's the position that undergoes electrophilic substitution quite readily, or it's somewhere where the metal is guided in by some other potential ligand atom. So here's an example of the directed metallation. Obviously quite complex sets of reaction conditions. The reason I put this in is to show that it is possible to get selectivity, but that it's also possible by changing the conditions in ways that are not entirely predictable to change the selectivity. So I have no rationalization as to why these are going differently, but here's an indole, the 2 positions marked in red and the 3 position marked in blue. If you use these conditions, palladium acetate, palladium 2, tertiary butyl benzyl peroxide, dioxane, acetic acid, etc., etc. How on earth anyone comes up with those kind of conditions, don't ask me. But it must have taken, I wouldn't like to have been the student who ended up having to examine a whole range of conditions before finding this one. Then you find that the selectivity is for the 2 position, so to make this red bond here. On the other hand, you make these changes, you still have palladium acetate, same percentage, but you don't have a peroxide in there, you have copper acetate and a different solvent system and very similar thermal conditions, but you can change the selectivity completely. Now I have no idea what the explanation for that is particularly. I mean, I've no idea exactly what all of these components in here are doing. I'm not even sure that Professor Gaunt knows. I mean, I know him, but I've never had a conversation with him to ask what he thinks is going on here. These are effectively recipes for getting different selectivity. And now you see it goes entirely to the 3 position, and reasonably efficiently. And that's indole, here is pyrrole, and the same sort of thing going on. The peroxide type conditions are favouring the 2 position, and well, actually these are peroxide, even less of a change here. Oh, I know, right, sorry, the difference here is the protecting group on the nitrogen of the pyrrole. This one is a withdrawing group, it's a carbamate. This one is a silyl group, which you could regard as more electron donating. But the difference of the nitrogen protecting group changes the selectivity dramatically, although actually this time the reaction conditions are the same. So all this is telling us is that you can usually get the selectivity you want, but you have to work at it by trying lots of different reaction conditions. In a way, that's the issue with CH functionalization. There are CH bonds all over the place, and different factors will decide which one is the one that takes part in the reaction. Here's some directing group assisted processes. This is another illustration of one with the directing group being an adjacent nitrogen atom. In this case, actually, there isn't another component. It's a dimerization through this position. But it's that position rather than any of the others around that benzene ring, because that's the one it's on the ortho position to the nitrogen carrying substituent. And it's believed, therefore, that at some stage you've got the nitrogen guiding the palladium in to activate that position, possibly via an electrophilic substitution mechanism. Here is a sort of a Suzuki reaction happening. It's this boric acid derivative, but there's no leaving group anywhere on here. The only thing that's happening that you've got is you've got this nitrogen, the same substrate, this nitrogen guiding in palladium, so picking out this system. Once you've got your organopalladium here, then the rest of the sequence will look like the Suzuki coupling. You'll exchange this cyclopropyl unit onto the palladium, and then you'll get a reductive elimination to join the palladium and the benzene ring. Okay, so I wouldn't, if I was you, what I would take away from the CH activation stuff is that it is possible to activate CH positions, so you don't necessarily have to have a leaving group in, like you have to in the Stille, Negishi, Kumada, Suzuki, Sonegashira set of reactions. The only difference with those, so with those you work to put in your substituent, but at least then you know exactly where the reaction is going to take place. On the other hand, if you've got some other factor which works in your favour, then you can more nowadays than used to be, you can get the CH activation to work. But of course you have to have something going for you, like natural selectivity, the right set of reaction conditions, or an adjacent directing group. So a knowledge of the catalytic cycles in the reactions where there is a leaving group is significant. With the CH activation, it's really just thinking, yes, it can be done if there is a reason for a particular CH bond being more activated than another one. But you wouldn't necessarily be able to predict that without writing down the structures and having a look at all the various conditions. Okay, so that actually is the end of what I want to say about palladium coupling. So basically the take-home message is those catalytic cycles for the organic with a leaving group, and then either a partner which has either tin, boron, zinc, magnesium on it, are all very, very similar to one another, that you can adjust these cycles to use, instead of an organometallic nucleophile, to use an oxygen or nitrogen nucleophile in the Hartwig-Buchwald types of reaction, but the catalytic cycle is still basically the same type. And then if things are in your favor, and more situations are being discovered where that works, then CH activation can also be a possibility. Okay, so that's the end for this morning. We'll start again at 2 o'clock, and if you remember, I said yesterday we'll do 2 sessions this afternoon rather than, and that's one less tomorrow, and then we can do the certificates. We'll have time to do the certificates tomorrow afternoon as well. Okay, so take your break now, and we'll see you again at 2 o'clock. again, I will forward all these notes to you once the internet's working, so I don't know